5.5, number 282. So some of these U substitution problems can get kind of sneaky. So I want to demonstrate some of the more difficult scenarios that you have to think about. So we have the integral of x cubed over the root of 1 minus x squared dx. All right, so our first guess is to let u equal what looks like the composition of 1 minus x squared into the root function. This is the most natural thing to suggest, and it's actually going to work, but I just want to make sure you realize what's going on with this particular scenario. So u equals 1 minus x squared. We now take du. du is going to be a negative 2x dx. All right, so what do we have now? Well, we know that u is going to fill in for the 1 minus x squared, so we have root of u down here. Dx, all right, dx on the right-hand side still has an x associated with it. Okay? So what I want to do, since I see that x here, I don't want to shift the x to the side. I don't want to combine variables. I don't want the x to be with the du. It would look very confusing probably. So what I'm going to do is this instead. I'm going to view this integral as x squared times x dx over root 1 minus x squared. And the reason I'm doing this is because x cubed has an extra x that I can use from it to be associated with the dx. It doesn't have to be x cubed as its own separate entity. I can think about it as x times x times x times dx. I can associate the x's however I want. So therefore I'm choosing to pick one of them out of the cube and associate with dx and leave the other one as x squared. And that's because I see an x dx here in the du expression. Right? Again, my goal here is to get all of the x's out of here and replace with some kind of combination of u's and du. So this will help that a little bit at least. Now I do still have an x squared left over to be accounted for, right? This will become u, root u down here. This will become ultimately negative 1/2 du. I can say that much at least. Negative 1/2 du equals x dx. Okay, so this x dx here is taken care of. That's taken care of. That's going to be u. This is going to be negative 1/2 du. One thing I have left to worry about is this x squared. So this is where sometimes you'll have to go back and reuse the original substitution in some way. Okay, I do have an x squared here, and it's related to u. Right? And I've only got a constant difference here. So this should work. Okay? So this x squared, reusing the original substitution, I will get that x squared is what? 1 minus u? 1 minus u. So I can replace x squared here with 1 minus u. And now everything will be in u in the next step. And that is really my goal. Okay? So I'll get the integral of 1 minus u, right? This is going to become negative 1/2 du, and that negative 1/2 I'll of course push to the outside in a moment. Those constant multiples I'm just going to shift out there so I don't have to deal with them. Cluttering up my integrand. And then I have root u in the bottom. I mean, it looks still kind of very convoluted, but it's a success as far as I'm concerned, because looking through it a little bit, you'll see that you have eliminated the difference, or I should say like this binomial basically, this binomial in the radical. The binomial in the radical is a difficult thing to take care of, and even though we now have a binomial up top, that's way better than the twofold problem of having a binomial in the denominator. Not only that, it's trapped inside a radical. Okay? So now I have a single variable inside the radical. It's a monomial. This is good. And the binomial situation has been transferred to above as well. This is also good. Okay, so we have 1 minus u over u to the 1/2 du. And now we're just going to use a little bit of algebra to finish this off. Again, there's no such thing as a quotient rule in reverse. So I've got to manipulate this somehow, and this is why having a monomial down here as opposed to a binomial is more successful. Because now I can split this up into two pieces, but with a binomial down here, I would not be able to split this into two pieces like I can this expression. Right, so I have negative 1/2, 1 on u to the 1/2, which will be u to the negative 1/2, of course, minus u on u to the 1/2 will be u to the positive 1/2. I hope that's clear. So now we just have a bunch of, not a bunch, but a couple power rules in reverse to take. Okay, so we get negative 1/2 on the outside, and the power rules will both bump up by 1 and multiply by the reciprocal. I move this one up by 1, it goes to 1/2. This one up by 1 is 3/2. And multiplying by reciprocals, I should have 2 u to the 1/2 minus 2/3 u to the 3/2 plus c, because I finished checking the integral. All right, and also you're probably starting to notice that I did not run the integral through both of these and apply the difference property for integrals, because it's just assumed you see that by now. You don't have to write it formally in that sense, right? Just go ahead and anti-differentiate each one separately. You know that's what would happen without specifically applying, you know, the symbols to each part of this difference. All right, so we need to change everything back to x because it's our indefinite integral. Started in x, we need to end in x. So replacing with x again, the u's become 1 minus x squared, the original substitution. So we get negative 1/2 to 1 minus x squared to the 1/2. I'm just going to write it like that instead of writing a root. It's fine. It doesn't have to be a root symbol per se. 1/2 minus 2/3 1 minus x squared to the 3/2 plus c. It can be cleaned up a little bit further. We can go ahead and remove this 2 and this 2 and this 1/2, and I can go ahead and negate both of these expressions. That way I'll have one negative floating around instead of 2. So I'll just push this one to the front because it will be positive now and it'll look nicer. Positive one first. 1/3 1 minus x squared to the 3/2, and now minus the first one, which is now negative, 1 minus x squared to the 1/2 plus c.